Okay, this is part 2 of Chapter 2's lecture. I'm going to pick up where I left off with the structure of water. So we've talked about ionic bonds and we've talked about covalent bonds. Covalent bonds are when you have the sharing of electrons. Ionic bonds typically would take place between two ions that have separate charges. Those are charged atoms that can have a negative or a positive charge. One of those charged atoms can either give up or donate an electron. The other one can either accept electrons. In the case we saw with the example of sodium and chlorine were the two elements that we looked at. So hydrogen bonds, as stated before, here you have 5 water molecules, and of course holding those water molecules together are hydrogen bonds. Water molecules are considered polar because you're going to have an unequal sharing of electrons. So if you look at this right here, let's look at water around the sodium chloride here. So here you have this water molecule right here. Okay, let me just tell you, we know water is H2O. It's a molecule in the compound, correct? All right. So you have 2 hydrogens which are in the white. Okay, this is the structure. And the hydrogens have a positive charge. This big red structure here is oxygen. So that's your H2O. Oxygen is negative. All right. So that's why it's polar. Water molecules are polar because they have an unequal sharing of electrons. Now, non-polar molecules, which we're going to talk about in another chapter, they have an equal sharing of electrons, but we're going to talk about that in another chapter. Here are some properties of water here that you need to be familiar with. Water, you have is considered a universal solvent. A lot of things can dissolve in water, such as table salt or sodium chloride, sugar, the C6H12O6, which is the molecular formula for sugar or glucose. Also, it has cohesion and adhesion, which means that the water molecules can cling to each other. And we're going to break each one of them down. If you look on page 30, figure 2.10, they're showing you a great example of both cohesion and adhesion of water molecules. They kind of cling together if you look at them. They're showing you adhesion. And the cohesive part, well, they have a high surface tension, high heat capacity, high heat of vaporization, which is why we sweat, and varying density are the properties of water. So, once again, water is the universal solvent. It's hydrophilic, which means that molecules are attracted to water. You've probably heard the term hydrophilic, or if this is your first time hearing it, it simply means water loving. Anything that will dissolve in water is considered a water loving molecule, a molecule that's attracted to water, which means it's hydrophilic. Hydrophobic, those molecules not attracted to water. Hydrophobic means, you heard of a phobia, means fearing, water fearing here. So things that are water fearing, that's not attracted to water, oil, things of that nature, butter, any type of lipid or fat, the skin on a chicken, the chicken fat, when you boil chicken in water, you see the little fat droplets floating on top. And water causes sodium chloride to dissociate, which means that sodium chloride, when you put table salt in water, the two elements or atoms or ions are going to separate from each other, which is why salt is able to dissolve in water. Okay, cohesion and adhesion. Cohesion, ability of water molecules to cling to each other due to hydrogen what? Bonding. Now, adhesion, ability of water molecules to cling to other polar surfaces. So you have the adhesion, cohesion, they can cling to each other. So if you look at the blood vessel that's coming out of the guy's bicep muscles or his arm on page 30 of your textbook, figure 2.10, you can see that water that he's consuming is going to flow through his blood vessels. However, those water molecules, they are going to what? The water to move forward, to flow in a forward way because of the adhesive property, allowing them to cling together, kind of like glue. When you, if you put glue on something and you want to connect it to something else or glue it to something else, that's kind of how it works. Adhesion, ability of water molecules to cling to other polar surfaces. Now, adhesion of water molecules helps prevent the backward flow. So once those water molecules are bound to each other polar surfaces, which would be like the blood vessels, you can look at the transport vessels coming through the roots of a tree, and those water molecules are going to be bound to each other, and those polar surfaces, of course, would be in the blood vessels and in the water transport vessels of the trees. So, water assists in the transport of nutrients and waste materials. Many multicellular animals contain internal vessels in which water assists the transport of materials. The liquid portion of blood, which transports dissolved and suspended substances within the body, is 90% water. So our blood vessels, blood travels through those vessels in the guy's arm. Of course, is 90% water. So that's your other polar surface, the blood vessel. And here's your example here. Cohesion, right here. The water molecules allow forward flow, the cohesion of water molecules in our blood or the blood vessel. Adhesion here, which is the same concept. Okay, it's going to prevent the water from going backwards, which means it's going to continue forward. Adhesion of water molecules help prevent backward flow. So it's the same, they're able to, water molecules are able to bind to other polar surfaces, which would be these two structures here. Properties of water. Water has a high surface tension, like, for example, this little water spider that you see here, or this water flea. Of course, because of the high surface tension of water and the hydrogen bonding that can actually hold the water molecules together, will allow this organism to actually cling or sit on top of the water without it sinking. So, that's a good example. The next one, I don't think this example is in your textbook. No, it's not. Water has a high heat capacity. Heat capacity and heat of vaporization. Okay, heat capacity. The many hydrogen bonds linking water molecules allow water to absorb heat without greatly changing its temperature. The temperature of water rises and falls slowly. So water has a high heat capacity. If you look at figure 2.11, in order to break these hydrogen bonds, we're going to look at A and B. Okay, water takes a large amount of heat to vaporize at 100 degrees Celsius. Okay, so if you have that pot of water, you put a pot, let's say it's your coffee pot, or you put something on the stove. Of course, it's going to take a lot of heat, a large amount of heat to allow those hydrogen bonds to break between the water molecules, and it's going to allow those water molecules to escape into the environment as because of its high heat capacity. It's going to evaporate into the environment. Heat is spelled as water evaporates. If you look at the guide, letter B, figure 2.11 on page 31, it takes much body heat to vaporize sweat. This is another example of vaporization. Okay, now when we sweat, that simply means we're releasing water from our bodies. Once we release the water and we sweat, this allows the body to cool down. So sweating is a good thing. Okay. It says if the heat given off by our metabolic activities were to go directly into raising our body temperature, death would follow. So we got to bring the body temperature back down to 98.6 degrees Fahrenheit or 37 degrees Celsius so we won't die or pass out, which is why we sweat. That water is going to evaporate from our bodies and it's going to be expelled into the environment. Ice is less dense than water, which is why it floats on water and not sink on water. It's a great insulator for a lot of those organisms that live in those extremely aquatic environments. So if you look at figure 2.12 in your textbook, they're actually differentiating between the ice lattice and, of course, the liquid water per se. And of course, you know, ice is heavier or has a higher density than the water, which is why ice floats in water rather than sinking. Acids and bases. Okay, here you need to understand what a base is and what an acid is. Okay, here we're going to look at the pH scale. The pH scale simply means that it measures the hydrogen ion concentration in a solution. So we need an equal concentration of both hydrogen ions and hydroxide ions. So here is an example of an acidic solution. When you have an acid, acids, of course, on the pH scale, if you look on page 36, well, not 36, page 34, figure 2.13, you can see the pH scale, and anything that's less than, that's going to go from 0 to maybe 6.5 is considered an acid. So anything less than 7 is considered neutral. Anything less than 7, of course, is considered acidic and has a high concentration of hydrogen ions. Lemon juice, vinegar, coffee, they release hydrogen ions. That's what acids do, and they accept hydroxide ions. Now here you have a base. Anything that's above 7 is considered a base. So if you look in the blue, and of course the numbers are bigger once you go past 7, those things are considered basic. Baking soda, stomach acids, milk of magnesia, household ammonia, bicarbonate of soda, oven cleaner, sodium hydroxide. So what these things are going to do, they're going to take up hydrogen ions, or they're going to release what? Hydroxide ions. That's the difference between an acid and a base. Okay, here's the picture here. All right. Anything less than 7 is acidic. Anything higher than 7 is basic. Of course, you can see the H+, those are your hydrogen ions being released by acids. The OH negative is a hydroxyl ion that's going to be released by a base. So they're going to be the opposite. Bases will take up or accept hydrogen ions. Acids, on the other hand, will take up hydroxide ions with that OH group, but it's going to release what? Hydrogen. Bases release hydroxides. Okay. Buffers and pH. Anything that's going to keep the pH from changing or swinging out of control is considered a buffer. I'm going to stop here, and I'm going to probably just give you guys an example of a buffer. A good example of a buffer, for example, is when you have acid reflux. Okay, People typically would take baking soda. They're going to take some type of Rolaids, Tums, some type of over-the-counter drug. And what's going to happen is the medication that they take is going to be considered a buffer, and it is going to remove those hydrogen ions out of your intestine or your digestive system in order for you to feel better and to get rid of the burning sensation that you have in your chest. Okay, so baking soda, of course, is considered sodium bicarbonate. If you look in, well, they don't have that in your textbook on page 34. But anyway, pH of blood, of course, buffer 7.35 to 7.45 is maintained by buffers in our systems. Is a really good example. If we did not have buffers in our blood, guys, the pH of our blood will fall out of that range of 7.35 and 7.45, and it could lead to coma. It could lead to death.